Okay, so we're going to work with two additional rules for logarithms. These are called the product and the quotient rules for logarithm. So let's see what we're going to do. We have the log of 6 is 0.778. We want to evaluate the log of 60,000. Well, we can write 60,000 as 6 times 10,000. And we can even further write it as 6 times 10 to the 4th. Now, the product rule allows us to separate this into a sum of two logs. So this would be the log of 6 plus the log of 10 to the 4th, where we're told that the log of 6 is 0.778, and the log of 10 to the 4th is 4. So that tells us that the log of 60,000 is 4.778. Now, the next one, we're giving the log of x and the log of y, log base 4 of x and log base 4 of y. And we want to use them to look at this problem. So we have 4x over y. So this is a quotient. A quotient becomes a difference of two logs. So this would be log base 4 of 4x minus log base 4 of y. However, if we look at this, we have log base 4 of 4x. That is a product, so we're going to separate it into a sum. So this becomes log base 4 of 4 plus log base 4 of x minus log base 4 of y. Log base 4 of 4 is simply 1, because 4 to the first gives us 4. We're told the log base 4 of x is 8.9. And log base 4 of y is 2.2. So combining these, we have 9.9 minus 2.2, or 7.7. Okay, the next problem involves the Richter scale. The Richter scale is one application of logs. Okay, so with the Richter scale, it's log of s over s sub 0. So that means that that's the magnitude of an earthquake. So the one in Chile in 1960, we have 9.5 equals the log of s over s sub 0. And for the one in Alaska, we have 9.2 equals log of s over s sub 0. So now, what we're going to be working with is the log of s for the Chile earthquake minus log of s for the Alaska earthquake. Simply gives us 9.5 minus 9.2, which is 0.3. But also this difference, if we put it back using the property we used before, this becomes a quotient. So this becomes the log, the intensity of Chile over the minimum divided by the intensity of Alaska over the minimum, which simply becomes the log of the intensity. Well, let's work it out. I'm not going to skip any steps. Chile over the minimum times S sub 0 over S sub A. Because remember, we're dividing fractions, so it's keep, change, flip. So this is the log of S sub C over S sub A. Well, the log of S sub C over S sub A is 0.3 because that's the difference in the values in the Richter scale. Now, remember, log is log base 10. So S sub Z over S sub A, or the ratio of the intensity of the earthquake in Chile over the intensity of the earthquake in Alaska, is 10 to the 0.3, which is approximately 2. So second log gives us 10 to the, and if we put in 0.3, it's 1.995, etc. So it's approximately 2. So the earthquake in Chile, or in China, no, Chile, yeah. Chile had seismic waves about twice the size as in Alaska. So even though the values on the Richter scale are not that far apart, the actual intensity of the earthquake in Chile is like 2 times the intensity of the earthquake in Alaska. Okay, another application of logarithms is decibels. So 10 times the log of E over E sub 0 is what we use. And that's the decibels. And it's working again with the intensity of the sound. So this one tells us French law limits smartphones to a maximum possible volume of 100 decibels. Normal conversation has a sound level of 65 decibels. What is the ratio of the sound intensity of the sound of 100 decibels to the intensity of normal conversation? So 100 equals 10 log of E sub S for smartphone, E sub 0, and 65 equals 10 log of E sub C for normal conversation over E sub 0. So if we subtract these two, so 10 log of e sub s over e sub 0 minus 10 log of e sub n over e sub 0 is 100 minus 65, or 35. So we want the ratio. We can divide out the 10, or factor out the 10. Equals to 35, dividing through by 10, we get that the log of e sub s over e sub 0 minus the log of e sub c over e sub 0 is 3.5. Well, again, using the property, we have a difference. This becomes a quotient. So this becomes the log e sub s over e sub 0 divided by e sub c over e sub 0, which, like we did before, simply becomes the log of e sub s over e sub c. So the log of e sub s over e sub c equals 3.5. So 10 to the 3.5 equals the ratio. And that's approximately 3,162. We do 10 to the 3.5, we get 3,162.27766. So by what factor has the loudness increased in going from normal speech of 65 decibels to a smartphone at 100 decibels? So it's an increase of 10 decibels (3.5 times). So it's doubled (3.5 times). So we take 2 to the 3.5 is approximately 11. So a smartphone at 100 decibels seems about 11 times as loud as normal conversation at 65 decibels. Okay, so we've had two applications of logarithms with the Richter scale and with sound, the decibels. Another application is with magnitude. So with good binoculars, you can see stars with apparent magnitude 9. The Hubble telescope, which is in orbit around the Earth, can detect stars with apparent magnitude of 30. How much brighter is the Hubble telescope than good binoculars, measured in terms of the ratio of the brightness of stars that they can detect? Well, our formula is 5/2 log b sub 0 over b. So we're going to work with this the same way we've worked previously. So 9 equals 5/2 log b sub 0 over b sub 9. We could say with binoculars or whatever. And 30 equals 5/2 log b sub 0 over b sub 30. So if we subtract them, 30 minus 9 is 21. 5/2 log b sub 0, b sub 30 minus 5/2 log b sub 0, b sub 9. We can factor out the 5/2. We have log b sub 0 over b sub 30 minus log b sub 0 over b sub 9. Multiplying both sides by 2/5, we get 42 over 5 equals log. And then putting this as division, b sub 0 over b sub 30 divided by b sub 0 over b sub 9, which means this is log b sub 9 over b sub 30 by simplifying. So b sub 9 over b sub 30 equals 10 to the 42 over 5, which is 10 to the 8.4, which is 250, 0, 0, 0, 0, 0, 0, approximately. So Hubble can detect stars that are 250 million times as bright as what one can see with good binoculars. Okay, so that's it for working with some product and quotient.